Hello Pre-Algebra students, this is Chapter 8.5, Slope-Intercept Form. In earlier parts of Chapter 8, we used intercepts to graph linear equations. Now we're going to graph linear equations in slope-intercept form. The graph of y equals 2x plus 3 is shown here. You can see that the line's y-intercept is 3, and that the line's slope, m, is equal to 2. Remember, m equals rise over run, or 2 over 1 in this case, which gives us a slope of 2. Notice that the slope is equal to the coefficient of x in the equation y equals 2x plus 3. This is our slope. Also notice that the y-intercept is equal to the constant term in the equation. These results are always true for an equation written in slope-intercept form. A linear equation written in the form y equals mx plus b is said to be in the slope-intercept form. The slope is always m, and the y-intercept is b. In our previous example, y equals 2x plus 3, our slope was 2, and our y-intercept was 3. Let's identify the slope and y-intercept of the line with this given equation. Y equals x minus 4. Remember, the x has an invisible 1 in front of it. Therefore, our line has a slope of 1 and a y-intercept of negative 4. In this equation, 3x plus 5y equals 10, we first need to solve for y to put the equation in slope-intercept form. So we'll begin by isolating y on its own side, and then dividing each side by 5 to isolate y. That will give us y equals negative 3/5 x plus 2. So this line has a slope of negative 3/5 and a y-intercept of positive 2. Now let's learn to graph an equation in the slope-intercept form. Our equation is y equals negative 2/3 x plus 4. The y-intercept is 4, so first plot the point 0, 4. We know the slope is negative 2 over 3, so we know that our rise is negative 2 and our run is 3. So we can begin with our point at 0, 4, and we can plot another point by moving down 2 units, rise of negative 2, and over 3 units, a run of 3, which takes us to 3, 2. We could continue plotting points using this same technique, and our next point would be down 2 over 3 at 0, 6. Now we can draw a line through the 2 points, and we have our graph of our linear equation. Okay. Here's the version of the graph from the text showing you the rise and run. Here are 3 checkpoint problems to try. Identify the slope and y-intercept of the line with the given equation. Use the slope and the y-intercepts to graph the equation. Press pause while you work. We're going to learn 2 more concepts when you return. Let's use the concept of slope and y-intercept to solve a real-life problem. The temperature of the Earth's surface averages about 20 degrees Celsius. In the crust below the surface, the temperature rises by about 25 degrees C per kilometer of depth. So let's first write an equation that approximates the temperature below the Earth's surface as a function of depth. To do that, we'll begin by writing a quick model. The temperature below the surface, which I'm going to label as temperature B, TB for temperature below, is going to equal the temperature at the surface, which I'm calling TS, plus the rate of change times the depth below the surface, correct? So our temperature below the surface is going to be equal to our Y. The temperature at the surface, we know, is 20 degrees C. The rate of temperature change is 25 degrees per kilometer, which is our X. So our equation in slope-intercept form is Y equals 20 plus 25X. Okay. The next part of the problem says that underground bacteria exist that can survive in temperatures of up to 110 degrees Celsius. Let's find the maximum depth at which those bacteria can live. All right? So if we want to know the point where Y is equal to approximately 110, we simply need to graph this equation. So let's do that. Okay, let's go ahead and graph. I've made a simple coordinate plane here where the values on my y-axis are by 10. So I have 10, 20, 30, etc. And my values here are 1, 2, 3, 4, 5, 6, 7. Okay? We know that our y-intercept is at 20. So let's go ahead and place that mark. And our slope is 25, which means that our rise is 25 and our run is 1. So we're going to move vertically 25 for every one step that we move to the right. So let's go ahead and mark that off. That's going to put us at about 45 and 1. We go up another 25, which puts us at 70 and 2. Now, as we go over to 3, we're going to go up another 25, which puts us at, where does that put us? About 95, correct? And as we go to 4, that's going to place us at 120, which overshoots our mark, correct? We wanted to know when we were going to reach 110 degrees. So let's go ahead and draw our line and then see if we can figure out where our 110 degree mark will lie. In typical Rachel graphing, this is not exactly straight, apologies, but you can get a rough sense of where the 110 degree mark will lie. And that is somewhere between 3 and 4. Looks like it's fairly close to 4. We can also then just plug our y value into this equation and calculate from there. So let's see if that gives us an answer that's close or somewhere between 3.5 and 4. So if y is equal to 110, we can solve to have 90 equaling 25x. 90 divided by 25 is going to give us a fraction that is equal to 3 and 15/25, which is, let's see, what will that reduce to? 3 3/5. Since this is a graph, we probably want that in decimal form, but for now that gives you a decent approximation that when x is equal to 3 3/4 kilometers, our bacteria are no longer going to be able to survive because the temperature will exceed 110 degrees. Now let's take a look at parallel and perpendicular lines on a graph. There's an important relationship between the slopes of two non-vertical lines that are parallel and between the slopes of two non-vertical lines that are perpendicular. If two non-vertical parallel lines are graphed together, they're going to have the same slope. For example, the parallel lines A and B in this graph, sorry for the blurriness, both have a slope of 2. Now let's look at the perpendicular lines. Two non-vertical perpendicular lines, such as A and C on this graph on the right, will have slopes that are negative reciprocals of each other. So notice line A has a slope of of 2, and line C has a slope where m equals negative 1/2. It is the negative reciprocal of 2. Let's go on and work through an example where we need to find the slopes of parallel and perpendicular lines. We're going to begin with the line with the equation 4x plus 3y equals negative 18. Our first step will be to write this equation in slope-intercept form. So let's do that first. Okay, so in slope-intercept form, our equation is negative 4/3 x minus 6. Now let's find the slope of a line that is parallel to this line. What will that slope be? Correct, it'll be negative 4/3 because two parallel lines have the same slope. So the slope of the line that is parallel to y equals negative 4/3 x minus 6 will also be negative 4/3. Now let's find one that is perpendicular. If the slope of the given line is negative 4/3, then our slope of a perpendicular line is going to be the negative reciprocal. So we know it's going to change from being a negative to a positive, so we can just leave that blank. And our reciprocal is 3/4. So if our line has a slope of negative 4/3, a line perpendicular to that line will have a slope that is 3/4. Here are your last 3 checkpoint problems for this chapter. For the line with the given equation, find the slope of a parallel line and the slope of a perpendicular line. When I see you tomorrow, we'll do more work with slope-intercept form and graphing equations that are in slope-intercept form. Have a great night.